since organic material was created in hundreds of locations throughout the Earth's surface at different times in different circumstances, we get different types of oils. In areas where the organic material wasn't buried as deep, in areas that were more shallow and were buried for a shorter time, we get heavier tar-like oil. If the organic material was buried really deep, a couple of thousand meters or so, we get more cooking, more digestic effect, and we get lighter, lower viscosity oils. In organic materials that were buried more than 6,000 meters deep, and for very long times, we get only gas. At that depth, the temperatures and pressures have destroyed or broken apart the molecules so that eventually only the small hydrocarbon chains of methane are left. Oil is found in reservoir rock, so let's turn our attention to what a reservoir is. In this section we're going to talk about reservoir rock properties. Rock properties are things like type of rock, the percent of oil in the rock, and the ability of that oil to flow out or through that rock. In the UAE, the most common reservoir rock is limestone. But the other common reservoir rocks are sandstone and dolomite, which are found commonly in many places throughout the planet. Oil sits inside these reservoir rocks. If you look at a piece of limestone or sandstone or dolomite with a magnifying glass, you will see little pores or holes that run through the rock. It is in these holes that the fluid, oil or gas or water, accumulate. The rock must contain some open spaces within the structure of the rock to hold fluid. The number and size of these holes within the rock determines its porosity, or pore space. We measure the porosity by the percent of space that is open compared to the space that is closed. If you have a porosity of 100%, you have pure fluid. You have fluid and no rock. Now, if you have 0% porosity, you have pure rock and no fluid. Igneous rock, or some minerals like diamonds, are good examples of zero porosity. They have no holes in their structure. A meaningful porosity, where oil is retrievable, is in the 5 to 30% range. Of course, bigger porosity percentage implies more fluid. Oil is found in sandstone and limestone, but it also can be found in shale. But shale has a porosity of about 1%, so the oil is very difficult to get out. Basement rock is either igneous or metamorphic rock and contains no oil. So if you are drilling and you hit basement rock, you are done drilling. Crude is found in reservoirs, not in underground lakes or pools, but in holes in the reservoir rock. These holes are called porosity, and its symbol is Phi. Here is a drawing with perfectly spherical sediment particles, all the same size, laid down symmetrically, so you get this uniform space between the particles, which would equal, in this example, about 48%. That is the maximum amount of porosity in any reservoir rock. Remember, though, that this is theoretical only. In the real world, where nothing is truly spherical or uniform, you would get less porosity. Sedimentary rock is made up of the accumulated sediment particles that have been squeezed and heated deep underground. If the grains of sand in sandstone are well sorted and rounded, they will have a porosity of about 25%. This type of porosity you would probably find in the remains of ancient beaches, because the waves pound the particles until the sand is ground down into uniform grains that are all about the same size. When sands contain grains that are of various sizes and shapes, all within the same reservoir rock, we say that it is a poorly sorted rock. These various shapes can decrease the porosity of the rock because there is less pore space, and the typical porosity for this type of accumulation is in the 5 to 15% range. A geologist's job is to note these types of rocks and report his findings, because in estimating the flow rate of a well, it is vital that the petroleum engineer understands the porosity of the reservoir rock. In this next example, you can see where the particles look like they have been cemented together. Cementing in nature is caused when sedimentary clays get wet and a chemical reaction takes place, literally cementing these rocks in place. Of course, cementing will decrease porosity because this cementing seals off the spaces between the rocks, reducing pore space, and not allowing any liquid to accumulate. So far we have been talking about intergranular porosity, or pore space between the grains. There is another type of porosity called vulgular porosity. This is where holes in the rock are formed. These holes are typically found in limestone reservoirs. Where do the holes originally come from in limestone? Well, after lithification, or rock formation, the limestone may have been lifted above the ocean level and exposed to fresh surface water. This lifting can be caused by things like earthquakes or plate movements. Fresh water, like rain, can mix with atmospheric CO2, causing carbonic acid. This acid water percolates slowly through the limestone and dissolves channels, causing anywhere from large chambers and caves to tiny interconnected networks of holes. Pore space cavities can be seen in this diagram, amplified by the green color. This porosity is called vulgular porosity. The third type of porosity is called fractural porosity. This is where the porosity is caused by fractures, where the rock actually breaks apart into cracks. These cracks contribute to the formation porosity by increasing the pore space. In fact, a technique in completion of an oil well is to pump down acid under very high pressure to help create these cracks. This is called well stimulation. So let's review. There are three types of porosity. 1. Intergranular porosity, where the porosity is caused by the spaces in between the grains. 2. Vulgular porosity, where the porosity is caused by holes that form in the rock. And number 3. Fractural porosity, where the porosity is created by fractures or large cracks in the reservoir rocks. Now, in order to be a good reservoir rock, you need the following characteristics. Number 1, porous rock. Rock that is filled with empty space containing fluid. Number 2, permeability. The rock porosity must be connected, channels between the pore spaces for the fluid to flow. We need fluids to be able to flow. Even though there might be holes or porosity in the rock, these holes must be connected. They must have little channels between them. We measure permeability in the laboratory using rock core samples. The unit of measurement for permeability is called the millidarcy, or MD.